Okay, let's look at question 5, November 2017. It's a work, energy, and power question. Here are all my work, energy, and power formulas. And there's some friction in this question, so I've got the formula for friction as well added to my work, energy, and power formulas. Okay, look here, just looking at the picture, we've got a system. 2 blocks, they make up a system. What happens to the one block happens to the other block. In the diagram below, a 4 kg block lying on a rough horizontal surface is connected to a 6 kg block by a light inextensible string passing over a light frictionless pulley. Initially, the blocks are held at rest. State the work energy theorem in words. Here's the work energy theorem. The net work done on an object is equal to the change in the object's kinetic energy. Okay, so system, light inextensible string. If this block moves, that block moves. If this block has a velocity, that block has the same velocity. When the blocks are released, the 6 kilo block falls through a vertical distance of 1,6 meters. Okay, so if this block is moving 1,6 meters, you must understand that this block is also moving 1,6 meters, and it's on a rough horizontal surface. So this block is going to experience some friction in its 1,6 meter journey. When the blocks are released, the 6 kilo block falls through a vertical distance of 1,6 meters. Draw a labeled free body diagram for the 6 kilo block. Look. Here's a labeled free body diagram for the 6 kilo block. Okay, we've only got 2 forces on the 6 kilo block. There's the tension in the string upwards and the weight of the block downwards. So let me see if I can scooch this in a bit smaller so we can get some more information on the screen here. Okay, so there's my labeled free body diagram for the block. Now it says to you, calculate the work done by the gravitational force on the 6 kilo block. So this 6 kilo block, the gravitational force is acting in which direction? Downwards. The 6 kilo block is moving downwards. So we can calculate the work done by gravity on the 6 kilo block if we use this formula. So let's put this formula in here. Come here, formula. Let's put the formula in here. So let's have a look. So the work done equals the force times the distance moved in the direction of the force, the displacement, times the cos of the angle between the force and the displacement. Sorry, I need to cough. So the work done is going to be the work done by the gravitational force. So the gravitational force is mg, the mass or the weight of the block. So the mass of this block is 6 kilos. The acceleration due to gravity, because it's mg, is 9.8. My delta x, it says to you that it falls through a vertical distance of 1,6 meters. And it is the cos of 0, because which way is gravity going? Down. Which way is the block going? Down. So that's why it's the cos of 0. So the work, if you have your calculator, remember the cos of 0 is going to be 1. 6 times 9.8 times 1.6 gives me 94,08 joules. That is the work done by the gravitational force on the 6 kilo block. Remember that work is measured in joules, so make sure you have the correct unit here. The coefficient of friction between the 4 kilo block and the horizontal surface is 0,4. Ignore the effects of air resistance. Use energy principles to calculate the speed of the 6 kilo block when it falls through 1,6 meters while still attached to the 4 kilo block. Okay, so like I said to you, this is a system, the 4 kilo block, the 6 kilo block. We can, if we know the speed of the 4 kilo block, it's the same as the speed of the 6 kilo block because it's a system. So we must consider also the energy of everything in the system when we look at this, because the energy of this and the energy of that are related. So whenever you do these things, remember that if you've got 2 blocks, you need 2 force diagrams. Why do we need force diagrams with this? We need force diagrams with this because the work is based on the forces. So we use the force diagram to figure out the forces, which then allows us to figure out the work. So if we have a look here, okay, we've got the force diagrams for the two blocks over here. If you have a look here, so the 4 kilo block has got its weight, obviously, it's got its normal, there's the tension in the string and friction, which is stopping the block moving. And if you look at the 6 kilo block, it's got the tension and the weight. So the tension here this way and the tension here this way, they're exactly the same value. Okay, so now using energy principles to calculate the speed of the block. If you have a look here at what is the work energy theorem here, okay, the net or total work done on an object is equal to the change in the object's kinetic energy. And that's actually what we're trying to find here, is we're trying to find the speed of the block, and we can use kinetic energy because kinetic energy is a half mv squared. Okay, so let's have a look here. The net work. How would we find the net work? We can find the net work if we look at all of the forces that are doing work here. Okay, so let's look at the 4 kilo block. If we look there, we've got the work done by friction. Okay, we've got the work done by the tension. We've got the work done by the normal. And we've got the work done by the weight. Okay, so these are all the things that are doing work, because we can consider that the tension is this dude over here for the 6 kilo block. The tension's working on both blocks, and this is going to be equal to the change in the object's kinetic energy, okay, which is delta EK, which is the kinetic energy final minus the kinetic energy initial. So let's go start having a look here at what sort of values we can put in for this network. Okay, so if we want to calculate this, we can start by putting this formula in here. Where did this formula go? Okay, so I've just explained that, but we're going to use this formula here anyway and write it W net equals delta EK. So let's start having a look what forces we've got. We've got friction. Okay, I'm going to come to friction in a moment. I'm going to show you the working for that. Let's have a look at the work done by the tension. The work done by the tension is actually equal to the work done by gravity on the 6 kilo block, because if you think about it, if we looked at tension as a force, looking at this diagram, okay, look at the 6 kilo block. I'm looking at this tension here, but understand that this tension here is the same as this tension here. So we can look at the 6 kilo block to work out tension. So this work done by the tension is actually equal to the work done by when the weight falls, because the work done by tension will be the mass of this block, mg, times by the distance it moves. And this whole thing moves 1,6 meters. I'm not explaining this very coherently, but that's how it works, that this the tension is equal to, the work done by the tension is equal to the work done by gravity, but it's in the other direction. So this value here, okay, 94,08 is the work done by the tension, and we can just insert it in here. And then we've got the work done by the normal. Now I ask you, which way is this thing moving? The work thing is going this way, okay. But is the normal going that way? No, the normal is at 90 degrees. So any force that is at 90 degrees does not do work. So this value is 0. Okay. Then we need to add in the work done by the weight of the 4 kilo block. This is also 0 because it's at 90 degrees to where we're moving, so it's not having any effect here. And now we need the change in kinetic energy. But the thing is, here we've got two objects with kinetic energy, so we have to consider them here. So it is a half mv squared final for the 4 kilo block minus a half mv squared initial for the 4 kilo block. Okay, I'm going to put this in brackets, and I'm going to put the the 4 outside the bracket to show you this is for the 4 kilo block. Okay. And then we have to add the same thing, the change in kinetic energy, for the 6 kilo block. Okay. We've looked at all of the forces and stuff here. So now I think we've looked at everything that's doing work here. Okay. We've looked at all the factors here, but we haven't figured out a value for friction. We've got a value for this, and then we need to substitute to put values for that. So the work done by friction, we need to find the force due to friction. What is the force due to friction? It's this. Okay, remember the force due to friction is the coefficient of friction times the normal force. So I'm going to substitute in here immediately for this mu kn. We got told mu is 0,4. Goodness me, this is not a good idea with this font. Okay, so I've got mu is 0,4, or it's mu k, times the normal force. What is the normal force? This is the simplest situation for finding the normal force. In this situation, the normal force is equal to the weight, which is 4 times 9.8, because the weight is mg. Okay, so how do we find the work? This is the force due to friction that I have here. It's the force times delta x, which is 1.6, okay, times the cos of theta, which is here the cos of 180. I've forgotten how to put in a degree sign. There we go. It's the cos of 180, okay. So we know that's going to work out to -1, because that's what the cos of 180 is. So friction goes this way, the block goes this way. So, and then we're adding the work done by tension, 94,08, and then plus nothing. And then now let's have a look here. What was the initial velocity of this block? They were both held at rest, so we're going to subtract 0 here with these. We are trying to find the velocity, that final velocity. So this mass here for this block is 4/2 of mv squared minus nothing, because remember the blocks were at rest. So now we've dealt with the 4 kilo block. Now we need to deal with the 6 kilo block. So that's the wrong thing. How do I put a half in here? I've forgotten how to put a half in here. My brain is tired. Okay, so this is a half of the 6 kilo block, and it's also the final velocity minus, and its initial velocity was also 0. Okay, so we've considered both objects that have velocity here. So now, in theory, we've looked at everything that's doing work here. Okay, and we've looked at everything that's got kinetic energy here, and we've said that the network is equal to the change in kinetic energy. So the network, we looked at all the forces that can do work, and we looked at all the things with kinetic energy. So if we get our calculator out here, and you know this is where you must check me, I get minus 25.088 plus 94.08 equals 2v squared plus, what is that, 3v squared, 3v squared. So on the right hand side there, we're going to end up with 5v squared and then I've got something like 68,992 equals 5v squared, and if we work this out, I get v equals 3,71 meters per second. no unit, no mark. And that should be your final answer.